this excellent book about gas. Here with us to speak about that topic, Dr. Goodstein. All right.
Okay, can everybody hear me? Okay. As Bob said, I wrote a book a few years ago, and by an astounding coincidence, it has exactly the same title as today's talk. Let's start out with some myths about energy. First of all, $4 a gallon is too much to pay for gasoline. The price has gone down recently, but it will go back up again, you can be sure of it. $4 a gallon is approximately $1 a liter. We pay twice that much for bottled drinking water. The fact is that gasoline at $4 a gallon is just about the cheapest liquid you can buy in the United States, and that's a big part of the problem. Oil companies produce oil, at least they say they produce oil. They talk about production, rate of production, and so on. In fact, no oil company ever produced a drop of oil. Oil was produced by the sun and the earth over hundreds of millions of years. The oil companies simply extract it and sell it, and that's why it's so cheap. We must conserve energy, otherwise we'll have an energy crisis. The law of conservation of energy is one of the deepest laws in all of physics. Energy is always conserved no matter what we do. We cannot not conserve energy. There are things we must conserve that they call fuel. When we run out of oil, the marketplace will ensure that it's replaced by something else. We will look very carefully at that argument in the course of today's lecture. There's enough fossil fuel in the ground to last for hundreds of years. We will look carefully at that as well. Nuclear energy is dangerous. At least many people think it's dangerous. Most technically trained people understand that nuclear energy is the safest, most dependable source of energy that we have, but it will not solve our problems, as I'll try to point out later. The greenhouse effect and global warming are bad. I claim that without the greenhouse effect and global warming, we would not be here. So let's go on. I'll start with a brief history of energy. In the 18th century, there was something called caloric. It was a conserved quantity, that is, it couldn't be created or destroyed. If you took a hot piece of copper and put it into a cool bath of water, you could predict how much caloric would run from the copper into the water and predict with confidence the temperature at which the two would come to equilibrium. So it was a precise mathematical theory, but not everybody agreed. And one of those who disagreed was named Count Rumford. He was born Ben Thompson in New Hampshire in 1753. He fought on the side of the British in the Revolutionary War, and so decamped to Britain and made it to Bavaria as a result. And the Count of the Elector of Bavaria named him Count Rumford. Rumford was the name of the town in New Hampshire where he and his wife had lived before the war. He did an experiment in which, he observed that the drilling out of gun barrels produced a great deal of caloric when none existed before, and that should not have been possible according to the caloric theory. He made an attempt to calculate how much mechanical action was equivalent to a given amount of heat, but that wasn't very successful. The law of conservation of energy was discovered at least 9 separate times between Rumford and its ultimate discovery. When something like that happens, the credit for making the discovery goes not to the person who discovered it first, but to the person who discovered it last, because he discovered it so well that it never had to be discovered again. And his name was James Prescott Joule. He reported in the 1850s to the Royal Society of London an experiment he had done, or a series of experiments he had done, one of which involved 14-pound weights descending through about 12 feet, one after another, and driving a paddle wheel in a bucket of water. And then after all had gone through, he measured the temperature of the water with a sensitive thermometer, and he reported that the amount of heat necessary to raise 1 gallon of water by 1 degree Fahrenheit was equivalent to the amount of work required to lift 800 pounds through 1 foot. And that constituted the discovery of the law of conservation of energy. There are a variety of forms of energy. One of them is kinetic energy, the energy of a car rolling down the street or a bowling ball rolling down the alley. Just because it's in motion, it has energy. But also the random motion of the atoms and molecules that make up the car or the bowling ball. That's a form of energy too. And the temperature of the object is directly proportional to the mean kinetic energy of the random motions of its atoms and molecules. So when the temperature of something goes up, it just means that its atoms and molecules are moving around faster. And then there's potential energy, gravitational potential energy of the kind that he endowed his weights with when he lifted them up through 16 feet. There's chemical potential energy, nuclear potential energy, and so on. There is one more form of energy that's important for our story, and that's radiant energy. The energy, the form in which energy reaches us from the sun across 93 million miles of almost nothing whatsoever. The upper curve here, the lower curve here is the temperature of a cool body. It radiates, like just everything radiates all the time. But a cool body radiates, and the radiation reaches the maximum somewhere deep in the infrared. The scale on the bottom is radio, infrared, a narrow range of colors that are called the visible, and then ultraviolet, X-rays, and gamma rays, and so on. The lowest curve reaches a maximum deep in the infrared and falls down to 0 again before it reaches the visible, so you can't see it. That might be the temperature of your own body. You don't glow in the dark because you're just too cool. The next higher curve is a temperature of a body that does glow in the dark. Its maximum is in the infrared. It moves down through the visible, highest at the red end and lowest at the blue end, so it looks red to our eyes. It might be the temperature of an ember in the fireplace. The upper curve, the uppermost curve on this is the temperature of the sun, and by no accident whatsoever, it has a maximum right near the visible. So our eyes evolved to be most sensitive to the temperature of the sun as it, light from the sun as it reflects off objects near us. Knowing that much, we can talk about the thermal behavior of the Sun-Earth system. The sun radiates energy at about 5,000 kelvins, uniformly in all directions. 93 million miles away, the tiny sphere of the Earth intercepts a tiny fraction of that. Of the fraction that is intercepted by the Earth, 30% is reflected, and 70% is re-radiated. It's absorbed and re-radiated out into outer space. The 30% that is reflected can be seen in a picture of the Earth taken from the moon, this famous picture, in the color of the polar ice caps and the oceans and the continents and so on. It's a simple calculation to figure out what temperature the Earth would need to radiate back into space the 70% that it must re-radiate. It has to radiate the same amount that it receives, otherwise it would be warming up or cooling down, and it's not doing that. So it has to radiate exactly the same amount that it receives. And it's a very simple calculation to figure out what temperature it would need to radiate everything that it receives, and the answer is 255 kelvins, or minus 18 degrees Celsius, or 0 degrees Fahrenheit. I claim that if that were the whole story, if the mean temperature of the Earth was 0 degrees Fahrenheit, we would not be here. We would never have evolved. But that isn't the whole story. The Earth's climate is governed by a number of factors. One of them is the tilted axis. When the Earth is at position A, the axis is tilted towards the sun, and it's summer in the north. When it moves around to position C, the axis is still tilted in the same direction because the Earth is a gyroscope, and the south is pointed towards the sun, and it's summer in the south. So the tilted axis is responsible for the seasons. The El Nino cycle is an interesting cycle. The trade winds blow across the equatorial Pacific, moving sun-warmed surface water towards the west, where it piles up against the Asian continent and creates the monsoon rains that are part of the climate of that part of the world. For reasons that nobody understands, once every 3 or 4 years, the trade winds slacken, the warm water spreads back out across the Pacific, and it causes droughts in Asia and Africa and Australia, and storms in North and South America, and a huge perturbation of the world's climate system. The thermohaline flow is particularly interesting. The water of the in the Pacific and in the Atlantic Ocean goes north along the surface. As it goes north, it gets colder because it's mixing with colder water, and also it gets saltier. Saltier. Both effects make it denser, and at a point a few hundred kilometers south of Greenland, it becomes too dense to float and it sinks. The water that sinks there will not reemerge for 1,000 years, but it runs back down along the Atlantic, around the tip of South America, and out into the Indian Ocean and the Pacific Ocean, and then comes up again. The offshoots of this thermohaline flow are thought to warm Western America and warm Europe, and it's a very important part of our climate system. But by far the most important part of our climate system is the greenhouse effect. The greenhouse effect takes place because the flux from the sun is 343 watts per square meter, averaged over the course of a year and averaged over the entire Earth. The oxygen and nitrogen of the atmosphere is fairly transparent to the hot radiation from the sun, so that goes through and warms the Earth, which then re-radiates the energy back out. But the re-radiated energy back out runs into molecules that it cannot bypass. Water vapor, methane, carbon dioxide, and so on are the greenhouse gases, the so-called greenhouse gases. They intercept the radiation from the Earth and re-radiate it back out into outer space where it's supposed to go, but also down to Earth, warming the Earth above the 255 kelvins that it would otherwise have. The 88% greenhouse effect that we had before the Industrial Revolution warmed the Earth to a temperature of 287 kelvins, or 14 degrees Celsius, or 57 degrees Fahrenheit. And at that comfortable temperature, we evolved, climbed down from the trees, and started building steam engines. There are important feedback effects in all this. For example, the warming due to greenhouse gases causes the polar ice caps to melt. The melting of the polar ice caps means that the Earth becomes less reflective, so more energy is absorbed, so that increases the warming even more. So that's a positive feedback effect. On the other hand, the melting of the polar ice caps might decrease the salinity of the northern waters and reverse the thermohaline flow that I told you about a minute ago. And if that happens, the result will be global cooling, not global warming. So this is a complicated picture, very complicated for a mere physicist like me. It's too complicated to go into in detail. We like to look at limiting cases. And there are two limiting cases. One of them is, suppose the greenhouse gases were stripped from the atmosphere completely. There were no greenhouse gases at all. The temperature of the Earth would immediately fall to 255 K. But it wouldn't stay there. At that temperature, all the waters of the Earth would freeze, and the Earth would become much more reflective and get colder still. There are theories that say that the Earth was like that deep in its history, perhaps 1 billion years ago. It's called the snowball Earth theory. The other possibility is that the greenhouse effect will increase from 88% to 100%. We don't know exactly what would happen then, but we have a model to look at, and that is the planet Venus. Venus is a little closer to the sun, so it should be a little bit warmer than the Earth, but that's a very weak effect. Venus could be very Earth-like in temperature, but it isn't. The Russians dropped a probe to the surface and found out that the surface was hotter than molten lead. It has a runaway greenhouse effect and a surface that will melt lead. So the Earth could be a frozen wasteland, or it could be a Venusian inferno. It is neither one. It is a Garden of Eden that we have the responsibility to protect and are not protecting very well. This shows the greenhouse gases. In the upper curve, the blue curve, is carbon dioxide in parts per million in the atmosphere. The lowest curve is methane. The green curve is methane in parts per billion in the atmosphere. And the central curve is the temperature. And you can see that the temperature tracks the greenhouse gases over the last 400,000 years remarkably well. The temperature settled down in the last 10,000 years near its high end, and it's during that period that civilization evolved. What this graph does not show you is what happened in the last 100 years, because in the last 100 years, the greenhouse gases have increased by a remarkable amount, 30% in the case of carbon dioxide, doubled in the case of methane. And if the temperature of the Earth follows those trends, the results will be catastrophic indeed. We are doing an uncontrolled experiment with the planet, with the climate of the only planet we have. It is a very foolish thing to be doing. So what are the sources of energy? Well, before 1800, we lived on light as it came from the sun. The sunlight warmed ourselves and our animals and provided food for us, and that was sufficient. Coal was known about and small amounts of it were used for various purposes. There were oil seeps, natural seepages at the ground, and so oil was known. And in 1800, Alessandro Volta analyzed swamp gas to be methane, the principal constituent of natural gas. So coal, oil, and methane and natural gas were all known about. The three fossil fuels were known about, but they were very little used before 1800. Then in 1800, well, in 1765, an engineer named James Watt was fooling around with a steam engine when he thought of a better way of making steam engines. And James Watt's better steam engines kicked off the Industrial Revolution. By 1800, railroads were being built, and railroads had a double whammy on coal. They needed coal for fuel, but they also provided stable roadbeds by which coal could be transported over large distances from where it was mined to where it could be used. That created a demand for lighting, because lighting hadn't improved much since antiquity, and for a while whale oil was popular as a source of lighting. But by the middle of the century, the whales were getting scarce, and Edwin Drake pumped the world's first oil well near Titusville, Pennsylvania, in 1859. At first, the oil was used for illumination and for lubrication, but in 1860, Nicholas Otto, a German entrepreneur, built the world's first gasoline-burning engine, and soon the oil was in tremendous demand, and oil wells were being dug all over the world to search for oil. The net result is we can no longer live on light as it comes from the sun. We are thoroughly dependent on oil. We have created a trap for ourselves because the oil will run out. This shows the distribution of known reserves of oil. On the left-hand graph, it shows where the oil is, and 2/3 of it is in the Middle East, 10 times as much as in South and Central America, 10 times as much as in Africa, 10 times as much as in the former Soviet Union or North America. The Middle East is the only important player. Everybody else is trivial. The bars on the right show how much reserves there are. The right-handmost bar shows the amount in 2001, and there were 1,000 million barrels, that is 1 trillion barrels of oil, in known reserves waiting to be pumped. So there's plenty of oil in the ground. That's the wrong way to look at it, as we'll see. Marion King Hubbert was a geologist who worked for Shell Oil Company, and in 1956 or so, he predicted that the U.S. dominance in oil would end around 1970. What he had was this kind of data up to 1960 or up to 1950, and it showed that the discovery of oil in the lower 48 United States had peaked around 1930, and discoveries had gotten smaller ever since. The use of oil, the extraction of oil, would follow a similar bell-shaped curve, but later, because you have to discover it before you can extract it. So it would follow a bell-shaped curve later, and he predicted the bell-shaped curve would peak around 1970. He was almost laughed out of the profession for making such a ridiculous prediction, but when the 1970 came along, he turned out to be exactly right, as these data show. The black points are the actual extraction of oil, and the red curve is the kind of curve that he used to predict the peak, and so he was exactly right. This shows the oil reserves and the rate of discovery. The left-hand graph shows the oil reserves and shows that the OPEC countries had a big increase in reserves in the late 1980s. The right-hand graph shows that there were no important discoveries in OPEC countries in the late 1980s. What happened instead was that OPEC changed its quota rules for how much oil each country could pump, based in part on their known reserves, and the known reserves appeared like magic out of nowhere. So these are not geological reserves, these are political reserves of oil. The right-hand graph shows the history of discoveries, and you can see if you fuzz your eyes a little bit that the discoveries peaked around 1960 and have been declining ever since. It also shows the rate of production or extraction of oil, which crossed over the discovery rate around 1980 and has been greater than the discovery rate ever since. We've been producing or extracting oil faster than we've been discovering it for the past 25 years. That means that the reserves should have gone down, but as you can see in the left-hand graph, the reserves always go up, and not only in the large step, but also before and after it. So those are very soft numbers. We have now the same kind of data that Hubbert had for the United States. We have it for the world, so we should be able to predict when the worldwide peak in oil extraction will occur. One such prediction is shown on the next slide. The upper curve is the same curve as you saw on the last graph. It's the rate of extraction of oil. The lower curves all add up to the upper curve. We went through a couple of dry runs for the peak in oil production. The first one was in 1972 when the Arab countries realized that the United States had maxed out and embargoed the oil for a while at least. The second peak came in 1979 with the Iranian Revolution. We recovered from both of those. The third peak is predicted in this graph. This was a prediction made in 1998 by Colin Campbell and Jean Leherrera. That's predicted to occur just about now. We don't know exactly what will happen when the peak occurs, but it will not be temporary. It will be permanent. It will be forever. You have to use a certain amount of caution in assessing a prediction like that because the numbers are very flexible. They used 1.8 trillion barrels for the total amount of oil that ever existed. Looking at the data today, I would say that 2 trillion barrels is a more reasonable guess, and that would put off the peak for a little while. A new technology is the equivalent of new discovery. It makes more oil available. The increasing price of oil, the oil increased in price recently. The increasing price of oil makes more oil available because more technology can be applied. And the reserve numbers are very soft, as we've already seen. And all of those things make these predictions dicey. But the basic idea is right. The basic idea is that the oil discovery starts from zero, rises exponentially to a maximum that will never be exceeded, and then falls forever. And we will be in trouble not when we pump the last drop of oil, but when we reach the maximum, because then the demand for oil will continue to increase, the supply of oil will decrease, and we'll be in serious problems. And that's the lesson to be learned from all of this. Kenneth DeFaze is an oil man, and he said he knew that Hubbard had been right and that the United States had reached its peak in the spring of 1971 when he read the following single line in the San Francisco Chronicle. The Texas Railroad Commission announced 100% allowable for the next month. You have to be an oil man to understand the significance of that. The Texas Railroad Commission was the quaintly named cartel that governed the price of oil and the use of oil by governing the rate at which oil could be extracted in Texas. When it announced 100% allowable for next month, it was saying that it had lost control of the market, that the Texans were free to pump flat out, and that the peak had been reached. Ever since reading that, I've assumed that the worldwide peak would be reached when the Saudis made a similar announcement. OPEC, the Organization of Petroleum Exporting Countries, was created soon after the Texas Railroad Commission lost its traction to do for the world what the Texas Railroad Commission had done for Texas and for the United States. And so it's been governing the price of oil ever since. But when the Saudis, and they've been governing by controlling the rate at which oil could be pumped in Saudi Arabia. When the Saudi Arabians maxed out, that would be the end of that, the end of their control, and the peak would have been reached. It appeared to have been reached on February 24, 2004. A story in the New York Times said, "Forecast of rising oil demand challenges tired Saudi fields" by Jeff Girth. The country's oil fields, this is a New York Times article, so it was very long, and each paragraph is contradicted by the previous paragraph. That's called balanced reporting. So it says, the country's oil fields are now in decline, prompting industry and government officials to raise serious questions about whether the kingdom will be able to satisfy the world's thirst for oil in coming years. Then it goes on to say, some economists are optimistic that if oil prices rise high enough, advanced recovery techniques will be applied, averting supply problems. But he takes it back in the very next paragraph by saying, but privately some Saudi oil officials are less sanguine, and so on. I don't know whether it will turn out that February 24, 2004 was the day that the peak was reached. We're much too close to the situation to be able to tell. We need some distance. But for those who knew about the Hubbard prediction, this was a chilling article indeed. On the other hand, on March 5th, 2007, a story in the New York Times by a different writer, Jad Murad, said, many oil executives say that peak oil theorists fail to take into account the way that sophisticated technology combined with higher prices make searching for new oil more affordable. And it goes on to say, typically oil companies can produce only 1 barrel for every 3 they find. This represents a tremendous opportunity, and so on. So this says that the crisis may not be upon us. It may be a few years away, but it will come. No matter what this article says, the crisis will come. It took hundreds of millions of years for the sun and the earth to produce the oil that exists. We've pumped away half of it in 100 years, and the peak will come at the halfway point in pumping, so we're close to it, and it will come. Who uses oil? Well, petrochemicals are an important use of oil. There are 6.5 billion people living on the earth today, most of them reasonably well fed. That's a consequence of something called the Green Revolution that occurred in the second half of the 20th century. The Green Revolution consisted in large part of using petrochemical fertilizers to fertilize the land. I don't believe that the 6.5 billion people now living on the earth could be sustained, much less the 10 billion people that are expected by the middle of the century, without petrochemicals, without oil. Stationary power plants use oil, but in that application it's more easily substituted by nuclear and coal, and so that's not a heavy burden. Home heating uses oil largely in the eastern United States, and it will be a tremendous burden on people who have oil-heated homes to pay the price of oil when the price goes up. But the most important use of oil is in transportation. Cars, trucks, planes, ships, and trains all run on oil, and it would be very hard to substitute in that application. This shows global energy consumption in 1998. It hasn't changed since that very much. The 3 fossil fuels, oil, gas, and coal, contributed 10 terawatts. Terawatts is the scale on the left-hand side. They contributed 10 terawatts in all, about half of that being oil. And there are a few other smaller sources of energy. The total was about 13 terawatts for the worldwide. The U.S. consumes 3.3 terawatts on 99 quads. A quad is a quadrillion British thermal units. It's a unit you will not hear again in this talk. The U.S. used 1/4 of the world's energy in 1998 and still uses 1/4 of the world's energy with 1/20th of the world's population. So we are profligate users of oil. Oops. The economists tell us that when the oil starts to run out, it will be replaced by something else. Let's look carefully at that argument. The oil that we use is light crude oil. When it runs out, there will still be oil, so-called heavy oil, and oil sands and tar sands. Heavy oil is what's left behind in an oil field when the light crude is pumped out. By applying more technology, you can always get a little more oil out of an oil field, but the more you pump, the heavier it gets, and so that's a self-defeating game. The tar sands of Alberta have been renamed oil sands to attract investment. And at today's prices, or yesterday's prices of oil, not so much today's prices, it could be mined at a profit, but it's mined. That is to say, it's not extracted by the way light crude oil is extracted. It's extracted from ore, which is mined, strip mined, in an environmentally devastating way. And then every 2 tons of ore produces 1 barrel of a substance that's not rich enough to be distilled into oil, so hydrogen must be added. So some of the world's largest plants for obtaining hydrogen from methane have been built in Alberta. And that's a characteristic of these possibilities as we go down the list. Each one becomes more expensive and more difficult to use. Natural gas is a very good substitute for oil. It can be made into a liquid fuel. But the Hubbard's peak for natural gas is supposed to be about 10 years behind the Hubbard's peak for oil, so it's a temporary solution at best. Shale oil is unborn oil. That is to say, oil is born when organic inclusions sank deep enough in the earth to be cooked into oil. If it sank too deep, it got overcooked and became natural gas. If it didn't sink far enough, it became shale oil. So shale oil is unborn oil. Shale oil can be turned into an oily substance by heating it in a retort in an environmentally devastating way. People who have invested hundreds of millions of dollars in shale oil have recently sold it off because it seems to be energy negative, no matter what you do. Methane hydrate is another possibility. It's methane trapped in a cage of water molecules. It's created when methane comes into contact with water at high pressure and low temperatures, close to the freezing point of water. Nobody knows where it is, how much there is, how it could be mined, and how it could be used. We know it exists. That's about all. And then there's coal. We are told that there's enough coal in the ground to last for hundreds, maybe thousands of years at the present rate of use. The hundreds or maybe thousands of years tells you right away, the estimates vary over a factor of 10 for how much there is, coal there is. It tells you right away that nobody has any idea how much coal there is. But the present rate is the biggest boondoggle of all. The largest deposits are in the United States, but there are very large deposits in Russia and China as well. It can be liquefied as a substitute for oil. That was done by the Germans during the Second World War. They had coal but no oil, and so they liquefied coal. But it's a dirty fuel. It comes combined with mercury, arsenic, sulfur, and various other things that are very difficult to remove. It's the worst possible fuel from the point of view of the greenhouse effect because it's pure carbon, and every carbon molecule turns into a carbon dioxide molecule. You'd have to increase the rate at which it's mined by a factor of 5 to replace the missing oil, because we saw on an earlier graph, we use twice as much oil as we use coal, and the conversion process is inefficient. But even that would not be enough, because it doesn't take into account the increasing world population, the fact that the poorer parts of the world want to live more like us, that is to say, they want to increase their consumption of energy. And finally, it doesn't take into account Hubbards peak, which is just as valid for coal as it is for oil. So I think that all things considered, if we throw caution to the wind and turn to coal as a source of fuel, that Hubbards peak for coal will be reached in this century. So what does the future hold? Well, there will be an oil crisis very soon. I don't know whether very soon means it's already upon us. The recent run-up in gas prices seem to imply that it was upon us, and the run-down in gas prices seem to imply that maybe it's not upon us, and it will run up again, and so on and so forth. But we're too close to tell whether it's already occurred or it won't occur for another 10 or 20 years. 10 or 20 years is nothing on the scale of human history. We or our children or our grandchildren are in for some very difficult times. If we turn to coal to replace the oil, the fossil fuels will all run out by the end of the century. And then, in doing that, will have unknown consequences for the climate of the planet, and is a very dangerous thing to do. In any case, once it all runs out, we will be left with only two possibilities, solar and nuclear. The problem of building a civilization based on solar and nuclear energy is an immense problem. It has social and political aspects that I can't speak very much about. It also has technical parts that I can speak about. One possible step towards the solution is conservation. Emery Levins of the Rocky Mountain Institute recently wrote an article about this. He says ultralight, strong materials will make it possible to save fuel. Hybrids, and particularly plug-in hybrids, will save a great deal of fuel. We can build more efficient buildings and factories. We can get fuel from switchgrass and poplar. And I've added sugarcane to his list because sugarcane is the one crop that's actually used for fuel in Brazil, not in the United States, but in Brazil. About half the fuel they use is alcohol made from sugarcane. We can use electricity more efficiently. We can have fee-baits. That means you charge a fee to gas-guzzling cars and rebate it to more efficient cars. That's the kind of meddling that our politicians are particularly loath to make, and so on. There are technological fixes for the greenhouse effect. One of them is a parasol at L1. L1 is the Lagrange point, about 1/100th of the distance between the Earth and the Sun, where a satellite could stay in orbit with a period of 1 Earth year. Putting up a parasol at L1 to intercept 2% of the Sun's radiation is an idea that would allow us to burn fossil fuels to our heart's content without worrying about global warming. It's a clever idea, but practically useless because, as we've already seen, the Earth's destiny is not governed by the flux from the Sun. It's governed by what we do with the flux. Sequestering carbon dioxide is another idea, and that's certainly a good idea. But where to put it is a big problem, and nobody has yet tried it. So Solar is bound to be an important source of energy. We already use a great deal of solar in the form of hydroelectric power. The immense weight of water at the bottom of a reservoir drives a turbine, which provides electricity. The water runs out, gets evaporated by the sun, and falls back into the reservoir, so it's a renewable source of energy. But hydro cannot be expanded to replace the missing oil because we've already built dams pretty much everywhere we can. So the world is saturated with hydropower as it is. It accounts for about 25% of the energy used worldwide, 10% of the energy used in the United States. Wind is becoming more important as the turbines become more efficient and government subsidies make them more affordable. But the wind is too intermittent and undependable a source to replace the oil. Biomass will always be important. It was the unique source of energy before the oil revolution, and it will continue to be an important source of energy, but it's very inefficient. Only about 1 or 0.2% of the sunlight falling on a given piece of land get turned into usable potential energy by biomass. So it's not a very efficient way of converting sunlight. The golden standard for converting sunlight is photovoltaics. To make the 10 terawatts of fossil fuels that we saw on the previous graph by photovoltaics would require 220,000 square kilometers of photovoltaic cells. I think that the total amount of photovoltaic cells made up at present would probably cover about 10 square kilometers. So making 200,000 square kilometers is a very tall order. It's a very difficult thing to do. On the other hand, the total solar flux is about 20,000 times the 10 terawatts. So we are awash in solar energy. We just have to figure out how to use it. We have not begun to figure out how to use it yet. In Scientific American magazine, in December 16, 2007, an article by Ken Swagel and James Mason and Velas Thankus said that you could replace the 10 terawatts or 15 terawatts actually that fossil fuel that would be in use by the year 2050 with solar power if you had a tremendous effort to harness solar power. Unfortunately, nobody is putting out that tremendous effort, and so it might be possible to do, but it's not being done. Nuclear energy is bound to be a part of the solution. Geothermal energy is a form of nuclear energy because the interior of the Earth is heated by natural radioactivity decay. Geothermal energy is used for space heating in various places, but it's not very useful for power except in a couple of places where the geothermal source reaches close enough to the surface of the Earth to be tapped, and then it usually quickly runs out because it doesn't get replaced fast enough. Fission is the kind of nuclear energy that we've been using, but to make the 10 terawatts of energy that came from fossil fuels out of fission would require 10,000 gigawatt plants. A gigawatt is about the biggest plant you can make. 10,000 brand new solar fission plants is almost unimaginable. And if you did that, the supply of uranium would run out in about 10 to 20 years. So that's not a very good solution either. Fusion is the other kind of nuclear energy. And the deuterium in 1 gallon of seawater makes a gallon of seawater equivalent to 300 gallons of gasoline. And so fusion is the ultimate hope for the future. But fusion power has been 25 years away for the past 50 years, and it's still 25 years away. And so, although a great deal of energy and time and money has been spent in trying to harness fusion energy, it seems an ephemeral dream. Transportation is going to be a problem because nuclear or solar energy is not going to be used for transportation anytime soon. However, advanced batteries can be made to drive cars. Hydrogen might be useful as a fuel sometime in the future. It's not useful at present. It takes the equivalent of 6 gallons of gasoline to make enough hydrogen to replace 1 gallon of gasoline. So it's not a very good deal at present, but sometime in the future it might be useful, particularly if fusion energy comes online and we have all the energy we need. Hydrogen would be useful, and other fuels can be made from hydrogen. So we understand the basic principles that would be required to create a civilization like ours, but we're not doing it. This is a picture of the United States at 23:15 Eastern Standard Time on 14th of August 2003, when a big chunk had been taken out of the United States by a falling power line in Ohio. If a power line falling in Ohio could knock out this much of the United States, we live in a very fragile civilization indeed. This picture was probably faked, but it serves to remind us in any case of how fragile our civilization is. We scientists make predictions. We analyze the situation, make a prediction. We don't expect the prediction, the outcome of the prediction to depend on our making the prediction. And we hope our prediction is right because that will show how clever we are. In this case, I'll make a prediction that's different in both ways. Civilization as we know it will come to an end sometime in this century when the fuel runs out. I hope I'm wrong, and I hope that simply making the prediction will help make it wrong, because some of you will go out and help to solve this problem. I wondered about what I could do to contribute to the solution to the problem. I'm just a physicist, and so I don't know the applied science that's required to do anything substantial about it. So I thought about it, and decided what I could do is write a book. The United Nations Intergovernmental Panel on Climate Change said global warming due to human activity is real. It's time to stop debate and do something about it. So that put an end to the debate about global warming. In the 2006 State of the Union address, the President said we are addicted to oil. In the 2007 State of the Union address, he said he called for a 20% reduction in oil use by 2017, clean coal, solar, wind, and clean, safe nuclear energy, plug-in hybrids vehicles, clean diesel and biodiesel, ethanol from wood chips, grasses, agricultural waste, and so on. And in the 2008 State of the Union address, he said to build a future energy security, we must trust in the creative genius of American researchers and entrepreneurs and empower them to pioneer a new generation of clean energy technology. Our security, our prosperity, our environment all require reducing our dependence on oil. So this shows that even the President of the United States, the present President of the United States, is aware of the problem, although he's not doing anything about it. And so I wrote a book, and I hope you all get to enjoy it. Thank you very much.
In the slides, there's a reference to terawatts.
Yes.
Those terawatt hours.
No, terawatts. Those are terawatts.
Terawatt is a unit of power, though, and
yeah, there was a
about energy. Can you kind of clarify how that interchange works?
Yes, the terawatt hour is the unit of energy, and terawatts is the rate at which the power is generated. So you have to have a terawatt for an hour to have an amount of energy, but a terawatt is the amount you generate. That was a plot of the amount that's generated.
So you're saying that we're using energy at a rate of
10 terawatts per year.
Terawatts, and then you multiply that by the number of hours.
That's right. That's right.
And that's the number of joules that we use. Right?
That's right.
Okay.
Yes.
I don't know if I came in late, so you might have brought this up at the very beginning. But there's been a lot of talk of clean coal technology, and I was wondering if you could kind of address how clean coal is. Well,
clean coal usually refers to coal with the arsenic and sulfur and stuff taken out of it, but not sequestering the carbon dioxide. The sequestering the carbon dioxide is a big problem, and nobody has addressed it yet. People talk about it, but nobody has actually addressed it and done anything about it yet. Yeah.
You mentioned that a lot of the oil sands, oil shales, and different heavier forms of oil are technically difficult to extract and expensive to extract. Can you just reflect briefly on how oil technology, extraction technology has changed over the last 50 years?
Well, oil extraction technology has changed tremendously over the past 50 years. We now pump in the deep ocean and so on. And so it has improved dramatically. And it will continue to improve. I have no doubt that it will continue to improve. But that will not make more oil for the Earth. The Earth has all the oil that was made over hundreds of millions of years by the Earth and the Sun. And when we use it up, it's gone. And that's the end of it. Yes?
You showed a slide with some of the ideas that Amory Lovins has been talking about, but I don't remember you making any comment on it, what contribution those actions might make.
Well, that will, doing everything that Avery Lovins suggests will stretch out the problem, but it will not end the problem. The problem is that we've used up in 100 years all of the oil that nature has made in 100 million years. The conservation program of Avery Lovins will stretch out the problem, make it a longer-term problem, but it will still be a problem.
There was an online question, which I'll try to read. Is it true that the average global temperature has decreased each year since 2003? And it also appears that temperature variations precede CO2 variations, not follow them. How do you explain that?
Well, I'm unaware of any decrease since 2003. It may have been because the temperature fluctuates up and down, and the long-lasting trend is up, but it may have fluctuated down. Also, there is the effect of particulates in the atmosphere, which tends to cool the atmosphere and works against global warming. And when we have less particulates in the atmosphere, global warming will go faster. What was the second part of the question, Mayor?
It appears that temperature variations precede CO2 variations, not follow them.
It's very difficult to tell whether the temperature variations precede or follow the CO2. They're much. I showed a graph of the past 400,000 years, and you can't tell from that graph which is cause and which is effect. And so I doubt that very much that that's the situation.
A couple more questions. I think one of them asks, are there any other countries outside of the U.S. Whom we should be emulating who are leading by example? And the second question was, I think you already mentioned CO2 sequestration, and just if you had any further comments on that.
Well, as far as any other countries we should be following, Iceland is a good example, but it just went broke. And so, so it's not such a good example. What happened?
All right.
And the second question was?
CO2 underground sequestration.
Oh, yeah. CO2 is very difficult to sequester. If you try to put away the 100 parts per million of the atmosphere that we've increased the CO2 since the dawn of the industrial age, it would require 1/10,000th of the volume of the Earth to put it away. And it's very difficult to see where we're going to get that kind of storage space. And so sequestration is a nice dream, but I'm afraid it's just a dream. Yeah.
I'd like your opinion on something. I realize that you're a physicist, but it also sounds like you've done a lot of research in this area and have talked to a lot of people. But to what extent does our behavior play a role in the solution? I'm talking about our travel behavior, our land use patterns. In the overall picture of this, you talked a lot about technology and alternative fuels, but to what extent do we just need to be changing the way we do things?
Well, we need to be changing the way we do things in order to conserve fuel. It's like Amory Lovins. All those things will help, and changing our lifestyle will help. But it will only help. It won't solve the problem. It will only put it off further into the future. And so the real problem is that we became addicted to oil, and the oil will run out. and there's no getting around that. Changing our lifestyles will not change that. Yes.
You mentioned that the solar energy can be a substitute for the oil in the U.S. How would be the case in states that are not sunny, like Oregon?
I can't hear you.
What do you do when it's not sunny?
When it's not sunny, you suffer. That's one of the reasons that solar energy is not the solution to all of our problems. Yes.
Of all the technologies that you mentioned as alternative sources of energy, such as wind, solar, or fusion, which one shows the most promise in the near term, and which one shows the most promise in maybe the long term?
Well, I think that solar energy shows the most promise in the near term. People are inventing all kinds of more efficient solar collectors and so on, and so that is a promising technology in the near term. In the long term, nuclear fusion is the most promising, I think. But it's got to be very long term, because nuclear fusion, as I said, has been 25 years away for the past 50 years and still is 25 years away.
I do have one more online question. What approach with the new incoming administration would you suggest? What technologies do we work with first? Do you think we need to have a challenge to the country like President Kennedy had for the U.S. to get to the moon?
Yeah, I think that we need a challenge like President Kennedy. President Kennedy challenged the United States to go to the moon in 10 years, in 1960. And we did it. It was a tremendous technological problem, but we managed it. We did it. And we walked on the moon in 10 years. We need a similar challenge to kick the fossil fuel habit now while there are still fossil fuels. Nobody has presented that challenge to the technological community or given us the resources to do anything about it, but that's what's needed. That's what's essential.
Granted that we can kick the fossil fuel habit in a certain amount of time, it took hundreds of millions of years for the fossil fuels to be created, and basically that's sequestered CO2 over millions and millions and hundreds of millions of years. Really the question isn't that we're going to run out of oil, but what are we going to do with all that CO2 if we continue to burn oil? I mean, we just can't do it.
Well, I don't know what we're going to do with all that CO2. The CO2 is going to warm the atmosphere and cause great problems, and I don't know what we're going to do.
So then it's an issue of really of behavior, wouldn't it be? Wouldn't it be an issue of behavior rather than?
No, it's not. It's not purely an issue of behavior. It's an issue of a form of behavior that we've become so accustomed to that we can't change anymore. And that is the burning of fossil fuels.
Any other questions?
Yeah.
You spoke earlier about the reliance petrochemicals on food production, and I'm curious if in your research or what you think the future holds in terms of our ability to feed the population of the world and what the consequences are going to be.
Well, I don't know. I can't answer the question. It involves predictions that are beyond my competence. If we cannot produce enough food for the peoples of the world will fight back, and the results will be terrible. I don't know what the results will be. Sorry.
Any last questions? So we'll thank our speaker again, but before we do that, I hope you'll join us next week. Mia Burke and Jay Graves and Rex Burkholder will be our speakers, and their title is Portland is Good, but Copenhagen and Amsterdam are Awesome. Lessons learned from the world's best large cycling city. So we'll see you next week, and let's thank Dr. Goodstein again.